Okay, now we will do something mathematical here. I hope most of you remember your. I know there is a most of the members here are teachers, and they do remember what we are talking about. They deal with it all the time. There are some people here who are not really regular teachers. So I'm assuming that everybody remembers something called differentiation. If not, uh, well, don't worry even if you don't know what differentiation is yet. Doesn't really matter much, because all you would need to know that when you differentiate a function numerically at a point, sorry, when you differentiate a function, not numerically, just when you differentiate a function, you're supposed to do this. You're supposed to increase the argument of the function x by some amount h. So the function, of course, becomes f of x plus h. Subtract from it the original value of the function at x, which means, of course, you find out how much the function has increased. You divide that by the increase in your argument. So basically, you're finding out for an increase in your argument, how much more, by how much more is the function itself increasing. So this ratio is basically the rate at which the function increases when you go from x to x plus h. Differentiation simply involves this taking a limit of this quantity as h becomes smaller and smaller. So most of you, of course, are familiar with limits, but if you are not, just think of this as making h very, very, very tiny. That's not really mathematically true, but that's close enough. So for a very tiny increase in h, how fast does the function increase compared to the increase you made in the argument? Now, as all of you would realize that this limit as h goes to 0, making h smaller and smaller and smaller, is something you cannot really do numerically. But what you can always do is approximate. You can take h rather small and ask what this is. F prime x is f of x plus h minus f of x by h. This is an approximation, of course. If h is small enough, then this is a reasonable approximation. This is called the forward difference formula for the numerical derivative. Before I go any further, let me warn you that this is typically the kind of thing which you're not really supposed to do, for the simple reason that if h is very small, x plus h and x are very close together. So f of x plus h and f of x are very close together, and subtracting two numbers which are very close together is not really a great idea, as everybody knows who has done a lab, or even if you haven't done a lab, you realize that since floating point numbers are not stored with infinite accuracy in a computer, trying to subtract two numbers which are very close to each other might give rise to huge errors. That apart, so that's a warning. You should not really do numerical differentiation unless you were forced to do it. But if you do, this is the kind of formula you could use. F of x plus h, take some small value of h, f of x plus h, subtract f of x, divide by h, and you've got your f prime x. That is approximately. Well, instead of using the forward difference formula, you'd also use something called the backward difference formula, which is essentially the same. All you do is, instead of subtracting, increasing x and finding out how much the function increases, could try decreasing x and finding out how much the function decreases, and then divide. So that, of course, would be f of x minus h minus f of x, and you would divide that by minus h. So you end up with this formula. That again is an approximation, which is expected to be reasonably good when h is small. Now, if you average these two results, the forward difference and backward difference formula, which means you just add these two and divide by 2, you get a formula which is called the central difference formula. F of x plus h minus f of x minus h by 2h. Which is essentially saying that you go to the left of x, go to the right of x, subtract the two results, and divide by the gap between these two values of x that you're using, which is 2h. Now, mathematically speaking, if you take the limit h goes to 0 in each one of these three expressions, you should end up with exactly the same result. However, numerically, there is a difference. It so turns out that the central difference formula happens to be much, much more precise than the forward difference or the backward difference formula. Now I'm going to just show you how to use Numpy, whatever we have learned about Numpy so far, to calculate and display the results of numerical differentiation very, very easily. So let's go back to my Python interpreter. And for this, what I will need is some function which I want to differentiate numerically, and preferably a function in which case I can differentiate by hand as well easily, so that I know whether I'm going close to the right answer or not. So first, let's create an array of x's which are equally spaced and with a small spacing, so that the spacing h is what I can talk about when I say when I divide by h in the numerical difference formula. So for this, we already have something called a linspace function, which I introduced yesterday. Right? The linspace function, np.linspace. What does it do? It takes an initial value and a final value. Let's say I want to calculate things from 0 to pi. So I'm starting at np.linspace 0, going on to np.linspace pi, and taking, say, 1000 elements. So 1000 points between 0 and pi, actually 999 intervals. The step size would be pi by 999. There's a gap between in each successive x. So I've just created an equally spaced array of x's, and I will have to create an equally spaced array of function values, and then use that to calculate my different derivatives. But one quick thing that I can do is, if I find figuring out how much the gap between successive elements is, it daunting, this calculation, although it shouldn't be, I can actually use this. Step equal to true. So red step is an optional argument. For linspace, two arguments are essential. One is the start value, the other is stop value. You don't give the number of points, it by default defaults to 50. But usually the most common applications of linspace is start, stop, and number of points. But in addition, you can have other optional arguments like red step equal to true, would really means here return the step size. Just to see what it does, let me just make this start with a smaller array so that you can see what happens. And let's explode this right now. Notice that what has been returned is not really an array. So can anybody tell me what this object that has been returned is? What is this object that has been returned? It's actually two things. If you notice carefully, there's an array which begins and ends here, followed by a comma, followed by another object. So can anybody figure out what's going on here? What is this object? Okay, what kind of object this is? Of course, type will tell us that. And here I can use a shortcut. I did not store the previous result in a variable, but I can use this underscore character, which is something which Python allows you to use to get back the last result. So if you have calculated something and you want to get it back, and if the very last one, you can get it back by using the underscore character. And what Python tells you is that, of course, that this is a tuple. Okay, the tuple with two entries. The first entry is an array, which is the array which linspace would have given us without the red step equal to 2 option. And the second thing here is, of course, the step size. So red step equal to true just tells Python or tells linspace, don't just give me the array of equally spaced numbers, also give me the step size. But how do I use it? Let's go back to the 1000 element that we wanted. Notice that this was, of course, a step size of 0.349, which is quite big. So for numerical differentiation, you need a much smaller step size than this. Now it's too. If I store this in Access, Access will not be the array; it will become the tuple, which has both the array and the step size. What I can do in one step is this. Here's something which Onabola talked about before. This is unpacking. This was a two element tuple here. I am unpacking this into two variables. The first zeroth element of the tuple, or which we colloquially call the first element, array, that will go on the first variable here. The Access will become the array. The 1th element, this one, not this one really, but the new value which I get because I have 1000 points now, is going to go into H. Just to check, it really is this number, which is okay, which is not 100th of this. Remember, this was really pi by 9 intervals. This is pi by 999, but roughly 100th of this. Not exactly, but roughly. So now I have an array of X's which are equally spaced, and I also at the same step, I also have found out the step size. Okay, now what I need to do is find a bunch of y's for some function. Let's say I want to differentiate sine square. Okay, so I want to find out sine square of x and differentiate that. So I now first create an array of 1000 elements, each element of which is sine square of the corresponding element of x. And notice, this is what is so great about Numpy. You don't have to write for loops or anything. You just write sine of x square and just does that almost magically. So now I have a 1000 element array which has the y values. So what I need to do is subtract y0 from y1 for the forward difference formula, right? It's y at the next value of x minus y at the previous value, y at this value. So I want to subtract y0 from y1, y1 from y2, y2 from y3, and so on. So how do I handle that? Just for that, let me just illustrate, to understand that, let me just illustrate this with a simpler, shorter array to begin with. I'm going to come back to numerical differentiation, but just to illustrate the technique, I'm going to take a look at some smaller array first, the 4-element array. Let's just say I want to subtract 1 from 3, 3 from 7, 7 from 9. And that, of course, will give me a new array, or should give me a new array. How do I do that quickly? I can, of course, do that by writing a for loop. And that's the kind of thing that anybody would do if they were trained in standard programming languages like Fortran or C. There's nothing wrong with using the for loop, except that Python gives you, especially Numpy gives you, a much more elegant way of doing the same thing. And not only is that elegant, it's actually faster. So this is what you're supposed to do. Just to remember, what you need to subtract from is 3, 7, and 9 successively. And what you need to subtract is 1, 3, and 7 from each one of them. But notice, I do this slicing. What do I get? I get the slice of A starting from element number 1, which means element number 0. This 1 here is dropped. I get 3, 7, 9. On the other hand, I want to slice from the beginning and drop the last term. Just to remind you, index of the last term is also -1. I could have used 4, but I don't need to. Not 4, 3, but I don't need to. I can just put in -1. -1 automatically talks about the last index. So this says start at the beginning, keep on going, but don't touch the last index. So I will get 137. If I subtract the second one from the first one, I immediately get 3 - 1, 7 - 3, 9 minus 7. Why? Because A1 colon is nothing but these three elements. A colon minus 1 is nothing but 137. And when you subtract these two, the subtraction, of course, is element by element. So it's 3 minus 1, 7 minus 3, 9 minus 7. That's it. So this works for our small array, which I use for illustration. But in order to use it, what I will do, I will simply use this idea for my big array, 1000 element array of y's, the function values. So what I will do is y's 1 colon. So starting from element number 1 till the end, minus y's colon minus 1. Take all the elements from the beginning, but drop the last one. When you subtract these two slices, you actually get element number of one of the original y's minus element number 0, element number 2 minus element number 1, and so on. And this is not, of course, a different derivative. Numerical derivative would be this divided by h. Because I want to differentiate, divide every element of this array by h. That's easily done. So I took a long time to describe this, but all you really needed were 3 steps. You had x's created by the linspace x's comma h. You had y's, and now you have ty's. Okay. To see whether this has at all worked, let me now plot this at least. And let me just do something else as well. Capital Dy's is, of course, a different array from small dy's. Capital D and small d are different. Python is case sensitive. So capital Dy's is simply an array which calculates, which stores actual second derivatives. And we know what the second derivative here of sine squared x is. It's just sine 2x. Right? So this is my exact result, which we know because calculus tells us this is what the derivative of sine squared x is, 2 sine x cos x or sine 2x. And notice, of course, that what we have done is calculated sine 2x for every element of the array in one single line and in no time at all. Okay. Now let's plot these two things together. The derivative that we have got and the exact answer. The numerical derivative that we have estimated, that's of course an approximation, and the exact answer. Let's plot them together and see what comes out. So let's first start by plotting the original function. Now, because I'm on this console, I think I will have to reduce this a bit, or the plt.plot x as ys. I'm plotting this. The plot will come out here. It's small right now. I'm going to, this is just the original sine squared x. Of course, you want to see the plot in a big way. Maximizing this will work. But right now, let me just do all of what I want to do, and then we'll put them together. So this is x's and y's plotted together. Of course, details of matplotlib will be handled tomorrow by Abhijitda. I'm just using the most rudimentary things to illustrate what's going on. If I try this, I'm going to actually face a problem. Okay, this is fine. This is the original array x's and dy's together. That is the exactly calculated first derivative. Oops, I made a mistake here, of course. That's my second plot. And if I try this, calculating my numerical derivative with x's, we'll get into a problem. Can anybody tell me why there is this problem? So any ideas why is there a problem here? Notice this is what this is telling us. Look at the error message. It's very easy to see. It's saying that when you want to plot x and y together, you of course expect x to have the same number of. You have to expect that every point has an x, every point has a y, right? So it must have the same number of x values and y values. Now, why is this different in this case? X has, of course, there are 1,000 elements. That's why it has shape 1,000 comma. The dy's, which is what is being referred to as y here, the second argument. The dy's, for that we actually sliced up y's, which has 1,000 elements. But I didn't take all of the y's. I took y's 1 colon. From that subtracted y's colon minus 1. What that means was each one of the sub-arrays that I subtracted from are 999 element arrays. So dy happens to be a 999 element array. So it's natural that you are not able to plot x's and dy's together. They have different sizes. And it's also natural, if you look at what numerical derivative is calculating, to calculate the derivative, you need the value of one step ahead, original value, and subtract the two, right? What that means that if you have a big array of function values, you can calculate the derivative at the beginning, at any point in the middle, but you cannot calculate the derivative at the last x value because there is no y value for the next x value, right? Your x values are finite in extent, right? Once you get to the final x value, what happens when you increase that by h, what value of y you get? That's not there in your y's. So whenever you do a numerical derivative using forward difference formula, you do not get the last derivative. What this means is that you should not actually plot x's with dy's. What you should plot is only those x's for which you have the derivative, which is all the values from the beginning with the last value dropped, because the last x value does not have a corresponding derivative from this calculation. You can't. Your last value is not there. Of course, it may not be very easy to see any difference here in the graph. Anyway, the graph is too small. So let me just plot graphs together so that you can sort of begin to appreciate this. X's comma y is the original graph. X's minus colon minus 1 comma dy's and x's, all of the x's and all of the dy's. Because dy's are not numerically calculated, they're calculated analytically, and I have a dy value for every value, capital dy value for every value of x. So this works fine. I'm plotting all of them together in the same graph. Now let me just maximize this screen to show you the result. This was the original sin square x function, and you would need horribly good eyesight to be able to pick out that there are actually two lines here, not one line. You can see only one line, because there's so much on top of each other that you simply cannot see the difference. So are we to conclude that this is exact and there is no error? Of course not. To see what the error is, what you really should do is something like this. Let's not bother with the original function. Just let's look at this. Instead of plotting all the x's and y's and the dy's and capital dy's together, let's just plot the difference, dy's minus capital dy's. Now, if you're paying attention, you should be able to figure out that there is going to be an error here. You cannot directly do the calculation like this. The simple reason that capital dy's has a value for every x's, so it's a 1,000 element array, not a 999 element array like dy's is. And to bring them on par, what I will do is drop the last value of dy's, which is, of course, the value for which there is no corresponding small dy's. And let's just plot the difference. Now notice that this looks pretty big, but notice what the size of the error is. It's 0.003 minus 0.0. There's an error. This, of course, the difference here is error in the between the exact numerical calculation, exact analytical calculation and the numerical calculation using forward difference. And this is, of course, what you have. It's a small value. It's less than one or less than one part in 100. It's actually around 0.003, between plus minus 0.003. It's reasonably good. Just to sort of illustrate what you would want to do to push this further, suppose you wanted to use a central difference formula. The central difference formula, just to remind you, is this one. F of x plus h minus f of x minus h. So instead of just increasing h by 1 and subtracting the original value of, x by x plus h and subtracting the original value, you move to the right of your x, move to the left of your x, subtract the difference between the two values, divide by 2/8. The one thing you have to be sure about here is this. This means that not only don't you have a result for your last x value, because there's nothing to the right of it, you also cannot have a result for the 0th x or the very first x value, because there's nothing to the left of it. So just like you dropped the last term from your x's array when you were plotting, here you have to drop both the first and the last term. So you can have your result for xs1, xs2, xs3, and so on, but you cannot have a result for xs0. I mean the 0th element of xs. And to get xs1, you have to actually take the y2 and subtract from it y0, right? To get xs2, you have to take y3 and subtract from it y1, and so on. In order to do this automatically, and this is where the slicing magic comes in. So let's call this a central derivative for y's. What you do is this. You take y's 2 colon, you start at y2 because that's what you need for xs1. That's the very first x value for which you have a central derivative. Subtract from it. So basically, remember the very first element of this slice is y0. Very first element of this slice is y2. So this is a difference which is going to be y2 minus y0 and so on. Of course, you have to divide this by 2 times h. So this is your central derivative calculated, again in one line. And just to see whether this works out, let me just, whether this is any better, let me just remind you that you got a plus minus 0.003 kind of error using the forward derivative. Here, you have to be a bit more careful. You have to plot this dcy's has only corresponding values from xs1 to xs last but 1. So this is the slice of x's that you have to use. And of course, the exact values were available for all x's, so you have to take the corresponding slice here as well. And okay, this is what the derivative numerical formula looks like. Well, can you make out that this is really, the shape of course is different from the two graphs. This was my previous curve, the error from the forward difference formula. But the error from the central difference formula turns out with this. Looks different, but what's more important, much more important, is look at the scale. It was 0.003 for the forward difference, is 0.000006 for the central difference. So this apparently simple trick, just take the forward difference formula and the backward difference formula and take the average. This average is going to, seems like a very simple-minded trick to use, but it actually is way, way more accurate than the forward difference formula. Why is that the case? Of course, anybody who knows a bit about Taylor series can actually figure out that answer very easily. The short answer is the error in the forward difference formula is of the order of h. Error in the central difference formula is of the order of h squared. And because h is a tiny number, h squared, of course, is much smaller than h. Where do I get these things from? A simple calculus, just Taylor series, nothing else. Just to illustrate this a bit with something else, let me move on to something which many of you have already know about. Let's say, okay, I'm not going to bore you with numerical integration. This is, of course, for my first year class. I'm not going to bore you with all the details here. But let me just point out that one way of estimating an integral, which as you all, or at least most of you know, can be interpreted as area under a curve approximated by a series of trapeziums. Right? And if you calculate the area of all those trapeziums, you get this formula. Function of value of the function at the beginning, value of the function at the end, average of the two, plus the value of the function at all the intermediate equally spaced points, times h, the size of or width of this interval. That is a so-called trapezoidal formula for calculating an integral numerically. This is not the best possible formula, but this is just one of them. And let me just show you how you would implement this using Numpy. So once again, let's not go into other things right now. This is the formula that we are trying to implement. So, and let's say we are going to try to integrate sine square x, the same function, so that I don't have to create a new set of y values. Would hardly take me much time, but why bother? I'm going to integrate sine square x from 0 to pi. So I already have the sine square x values from 0 to pi at 1000 equally spaced points, so 999 intervals and so on. I also know the step size and everything. So what I need to do is this. Remember, I need f of a and f of b, the two endpoints. So y is the very first 0th or the very first element in the array y, which is actually sine squared of 0. And the sine square 0, of course, array that way. Take the very last element, which is f of b. You take these two things, multiply that by 0.5. That gives you the 0th f of a plus f of b is 2. To this, you have to add the sum of all the other y values. So this sum is a built-in sum. You can also use an np.sum, which is actually faster. So you can use a sum function from the Numpy module, which actually is more powerful and faster and can do other things as well. But right now, I'm just using it to sum up. Now, what I need to do is add up all the elements of y's except for the 0th element and the last element, which is where slicing makes life very, very easy. You just slice like this. So you slice, dropping the 0th element. That's why you're starting at 1. And remember, the slice will not touch the stop variable. -1 is the last element. So you're slicing from the 0th till the last bud 1. So that's your slice, and you're just adding it all up by using the np.sum function. np.sum just adds up all the elements of the array. You're doing all this. You're going to multiply the whole thing by 8. And you're done. That's your trapezoidal formula for the integral. By the way, I hope many of you can immediately work out what the integral is exactly, right? Sine square x dx from 0 to pi. And the answer is, of course, pi by 2. That's the exact answer. Let me just check what I get when I divide this answer by pi, which is stored in Numpy module as a constant np dot pi. I'm getting 0.5. This is exact. Well, nearly exact. That's really fortuitous because for trapezoidal, you don't expect to get an exact answer from most functions. Here you get an exact answer for a very good reason, very good geometrical reason, which I will leave well, the audience to figure out. Why did this give me an exact answer here? I wasn't exacting an exact answer on general ground, but because this function is sine square x, which is a particular kind of shape, the trapezoidal result actually gives me an exact answer. That's more of an accident, but usually it comes pretty close to the right answer, if not not exactly the right answer. But just to show you that there is an error which you would usually expect, let's do something else. Let's take a simpler function, x to the power 4, let's say. And let's say I start with x from, I change the x's array. I'm doing the entire calculation again for an integral of x of 4 from 0 to 1. So 0, 1, let's say 100 points. Smaller the number of points, of course, more the error. So this will make it easier for you to see that there's an error. Once again, because of the rest step equals true, of course with capital T, that's a Boolean constant. Because I'm using rest step equal to true, I'm going to be able to get both the array and the step size, and I'm unpacking them into these two variables. And I want to integrate x to the 4, so I just calculate the array x to the 4. And now I use this result. Okay, I don't have to type it all over again. But just to remind you, this is the beginning value of y, this is the final value of y, 2 endpoints. Sum them, half them, and add the rest. And then adding the rest is done simply by using a slice. And you take the whole thing and multiply by 8 step size. By the way, this is x to 4, whose integral, of course, is 1 by 5. From 0 to 1, the integral is 1 by 5, 0.2. Well, it's coming to be pretty close to 0.2. The exact answer is 0.2. The trapezoidal rule gives us 0.20034, etc. So not too bad. Of course, you are using 100 points. If you were to use 1000 points, which is easy enough to check, this is something you can check for yourself very easily. Just change one line. Of course, remember to recalculate the y. Now you see the error has decreased a lot. So this was 0.230. So this was correct to the actual value 0.2 with a gap of 0.00003. Here is 0.0000003. So the error has been cut down by a factor of 100. This is again something which we expect from the basic theory. Just to show you that you can do more complicated things with this, let's say let me try doing the trapezoidal formula. This, of course, is derivation, sorry, the Simpsons 1/3 rule. This, of course, is derivation. Let's not worry too much about that. The result for the Simpsons 1/3 rule, and the name 1/3 is because there's h by 3 in the front, is this. First of all, you need an even number of intervals, which means an odd number of points, by the way. Even number of intervals is needed for Simpsons 1/3 rule. And the area under the curve is approximated by this, h by 3 times f of a plus f of b. So the two endpoints, or y is 0 and y is -1, will just have to be added together. Then you have to take the odd numbered positions. So if at function value at 1, function value at 3, function value at 5, function value at 7, You take the odd numbered positions, multiply them by 4, and then you have to take the even numbered positions, apart from 0 and the final 2n, which A and B are. Apart from those, you have to take all the even numbered positions, multiply them by 2. So that is the Simpsons one-third rule. The two endpoints plus 4 times the odd value of the function odd numbered positions plus 2 times the value of the function even numbered positions. And now, just to check what this will happen, what will be the case here. Unfortunately, I cannot really use Simpsons one-third rule for the x's and y's I have right now because I've been using, say, 1000 points. 1000 points means 999 intervals. That's an odd number. So what I want, say 100 intervals, so 101 points. So the Simpsons one-third rule formula will simply be this: h by 3 times zeroth beginning value, final value, plus 4 times the sum. Of course, for that I can use np.sum or ordinary sum will do just as well for this particular purpose. But I need only the odd numbered points. So I need to slice wise in such a way that I get only the odd numbered points. The points wise 1, wise 3, wise 5, all the way up to wise 99. How do we do that? We start at 1. We don't go till the end. Of course, that ending point is actually point number 100, which is not an odd point anyway. You have to go up to wise 99. But you go in steps of 2. This is something I did not talk about before, but you have seen this before when Onaboda talked about slices for this. You can have slice indices, 3 slice indices, but that would mean start, stop, increment. So start at wise 1, then go in steps of 2. So 1, 3, 5, 7 until you hit or just touch, or rather just don't touch wise minus 1, the last one. So that gives you all the odd numbered elements sliced together, and then you are summing them up. Inside the bracket, that's 2 times. Because inside the bracket, because the whole thing has to be multiplied by h by 3. Well, I need only the even number positions here. I don't need the last one, which is also an even number position, but that's already taken care here. And I want to go in step 2 again. And that's your Simpsons one-third formula. Any other programming language would have made you write a lot of loops and etc. for this. This is what you get, very straightforward. What did I do wrong? Of course. Okay. Can anybody tell me what I did wrong here? I'm getting an entirely absurd result, right? I expected 0.2. I expected a result which is much closer to 0.2 than the trapezoidal formula. It's actually giving me 1.99. So can anybody tell me what I did wrong? Of course, you did something wrong. Formula is simpler than that if for loop or list comprehension method is used. Not at all. This is way simpler. If you use a for loop, you just have to write everything out. Here, all you are saying is you are writing it all in one piece. You can write it in 3 pieces if you want. That's why it's looking long. The formula is straightforward. All you're saying is the first 2 points. This is what would have required you to write a whole for loop. So if you think it's simpler to write a for loop instead of just adding these, just as writing a sum with a slice, I'm sorry, that definitely is not true. Of course, with a for loop, you would write this term separately, this term as a separate for loop, and this term as a separate addition. So each piece, when you put them all together, this looks a lot longer. This is just one line. Instead of many more lines of code which you would need with a for loop. And more importantly, this is way, way faster. But what is wrong with my calculation? Can anybody tell me that? Exactly. Vijay Paul has got exactly the right answer. I changed the access array. Of course, the access array now is a new access array. But I kept on using the same old wise array as before. So I should have actually changed the wise array first. This is the new access array, new wise array, and then I should have calculated this. So this is the Simpsons 1/3 rule result for the integral. Just to compare trapezoidal rule formula for this same calculation is this. This was pretty good, but notice that this is way, way better. The exact answer being 0.2. Of course, there are other ways of doing integration, things like Gauss integration and so on. Again, something which can be very easily implemented in Numpy using 3 or 4 lines of code, which would have taken lots more effort to implement on other systems. So I will not talk too much about Numpy any further because, frankly, that's a whole, well, that could be the whole workshop, talking about Numpy and what you can do with it. You will see more applications of Numpy in the coming days, especially tomorrow when Obijita talks about matplotlib. Then you will see about what happens when you use even pandas, and in the final day, when near the final end, when I talk about machine learning, I will also use Numpy a lot. But basically, these multidimensional arrays, slicing, the fact that you can use functions over the entire array without using an explicit for loop, not only does that make your code look simpler, it's actually a lot faster to use. Basically, because it's very optimized for your machine. So all these things are the huge advantages of Numpy. I did say that I would talk about scipy a bit, but I really will not talk about scipy very much in this lecture, simply because I have around 15 minutes left for this, and scipy itself would take 3 or 4 lectures, whole lectures. But let me just illustrate one thing to you. Scipy actually has scipy is another module which is called Scientific Python. It's built on Numpy. It uses Numpy in a big way, and scipy actually provides you many functions which does many of these calculations almost trivially. So say let me just show you one module in action. One submodule of scipy is huge, so I'm just going to take one submodule of scipy here, and just to make typing easier, I'm going to import the integrate submodule from scipy as si. Okay. Now si actually has this si, which is scipy.integrate, has many methods in it, which has to do with integration. Help will tell you a lot of those things. It's scrolled entirely off the screen, of course. Big help. So big that has actually gone way beyond this. So I won't be able to. But let me just point out one thing. In the examples here, okay, let me just try to see whether I can find one of the examples. Yeah. Okay, maybe let me just show you the documentation here. That will be easier. Let's just try to find out scipy.integrate documentation on the web, simply because it's way too big. If you just type out scipy.integrate in Google, for example, you'll immediately get the standard documentation. You'll see that it has many integration routines here. Something called quad. Then you have routines for double integrals, triple integrals, Gauss quadrature. Quad actually is something called Gauss Cronrod quadrature. Then you have traps, cum traps, cumulative trapezoidal, Simpsons, and so on. So let me just so there are the documentation actually shows that you can do many complicated things with it. Let me just go back and ask about so traps is a function which I saw there. So documentation is pretty clear. So the reason why I'm showing you this is nobody actually memorizes everything about all these functions. Whenever you need it, just look up the documentation. That's it. Documentation, by the way, is already there in your own machine. It's just that with the enlarged font I'm using right now, it's difficult to read the documentation there. It's easier to just read the documentation from the net. So what it says is scipy.integrate.traps takes in this one variable, one argument has to be given, which is the y values, the function values which you want to integrate. There is another one which is x, then there's dx, and so on. It's pretty simple. It doesn't have many choices. So let's see what this really does for us. So just to remind you, we had this access array of 100 elements between 101 elements between 0 and 1, so 100 intervals. We had the corresponding y's values. We have fourth powers of those numbers. And if I want to use scipy.traps, which is trapezoidal integration for this, you just have to call it. Give the y values and the x values. And the trapezoidal integral is calculated. So this, of course, this means that you don't have to remember the trapezoidal formula. You don't have to write that Numpy code for it. Of course, you don't have to write loops, etc. for it. Traps just does the integral for you. For people who are learning numerical integration, it's better perhaps to write explicit code using Numpy and then learn the shortcuts which you can use here, like just use the traps function for the psi module, which will immediately give you the answer. Well, there are some other details. For example, you could also, instead of specifying y's and x's, you could specify the value of dx here is h, right? So I've just said dx is the same as h and gives you the same result. You can actually call it with just y's. Then you get a very wrong answer for the simple reason that if you just give y and do not give x and do not specify what dx is, by default dx is assumed to be 1. Of course, dx is 0.01 here, 1 over 100. So assuming dx equals 1 gives you a result which is wrong by a factor of 100. But that's just the way the function is defined. If you do not give x, you better give dx. If you do not give dx, it is actually. Remember, when I've given x, I've not given the one single number, I've given the entire array. So an array of x values, the corresponding array of y values. The y values are the first argument, x values are the second argument. I can actually use Sims function, which is also there. And this gives me the Simpsons rule integral. There are many more options, etc. to this. And if you're interested, I actually have a set of videos on numerical integration, numerical differentiation and stuff in my YouTube channel. You've already seen the same channel where you're seeing the playlist for this, but these for the videos for this particular workshop. On the same channel, there are other playlists, including a playlist on using Numpy. There are some more details out there. So I will just take a break right now, and I'm also getting a call. So I will ask Kishore to take over for the time being, and if there are questions, I'm going to answer them, and then Ona Bodha is going to take over for the next part.
I think right at this moment we should take a break of 10 minutes, and then Arunaboda will take the charge. By this time, question may be continued, and Arunaboda is here to answer the questions. Thank you.
I can see one comment by Shuporna. She said that in order to take the difference, we can use a method called diff. Yeah, we could operate np.diff on the array to get the successive differences. She's quite right.
Yeah, that's right. I just wanted to show you that slicing achieves the same purpose, and
Right.
especially because you can use slicing for other things as well, like second derivative formula, or diff actually can also calculate second derivative differences. But there are many other calculations, like say you want to solve the Laplace equation on a computer using the averaging technique. Just
Yep.
slicing will do it for you. You don't have to do much more. So there are special things that you can use for each one of them, but but learning special things for each application becomes a bit difficult. It's easier to remember just the basic stuff.
Ranjan Dash commented that can we show the convergence of the integration formulas by increasing n?
Yes,
Yes, of
of
course.
course.
Why not? I mean, you can plot a
Because,
graph and see yourself.
of course, if you increase n way too much, there will be a problem, because if you increase n way too much, you are actually calculating more and more. Remember, more time,
Random
every
errors
time you
being
calculate,
taken.
you are going to have numerical errors because of the finite representation of floating point numbers. So if you do too many calculations, then your improvement in accuracy might actually go wrong. Then you might
But
start.
it will be a good
Worse.
exercise to see this
Yeah, it's
thing.
a
Yeah.
very good exercise. You can of course check this. If we did show this for numerical differentiation, for numerical integration, why not? Same thing.
Any other question?
Partho apparently has a question. It means every time we need to perform integration within two limits, we need to generate arrays accordingly, containing given number of elements. Of course. Um, well,
Sir, I have a question.
mhm,
Yeah,
yeah.
sir, we just learn how we differentiate any differentiate any function. Now, if I wish to calculate some higher order derivative, then what is the better way? Is it Taylor series expansion or
Well, these results are from Taylor series expansion. The point is, if you can calculate a derivative analytically, you should do that. Okay,
okay?
numerical differentiation always is more prone to error than other numerical algorithms, simply because subtracting two very similar numbers, very close numbers. This is
Actually,
very
I
with computers or Python. This is simply standard logic. Two numbers which are very close to each other, you subtract them,
uh,
you end up with a bigger error.
yes.
That's something I've seen also in labs, right?
Yeah.
However, let me tell you this: if you want to calculate higher order derivatives, you can numerical. Sometimes you have to. And well, let me just show you one thing. I hope my slides are still visible. They are,
Yeah.
right?
Mm.
This was the entire. Okay, this is the mathematical stuff behind all this. But higher order derivatives. This is for actually the lowest order formula. This one at the bottom here.
Yeah.
It's a standard second order derivative formula, which you can easily calculate using the slices.
Slices, right?
Y is 2 colon plus y is colon minus 2 times y is 1 colon minus 1.
Yeah.
One line. However,
Yeah.
these are called actually, okay, this is called this is the order a square formula. In fact,
Yeah.
even for first order derivatives, there are higher order numerical derivative formulas, things which use x plus h, x minus x plus 2h, x minus 2h, x minus 2h. They're called 5-point derivative formulas. Then let's take a look at them. They're all derived ultimately from the Taylor series.
Taylor
So
series, right?
one place where you actually have to use numerical differentiation is when, say, perhaps you don't have an analytical formula available, you just have the values. And say when in our lab, we have an air track which find the position of particles from time to time and measures the positions automatically. But the velocity and acceleration are calculated using numerical derivatives. Then you have to. If you have to use numerical derivatives, then you do it. Otherwise, you don't. That's the standard rule.
Actually, I have an experience about that. I am familiar with Fortran, and I try to calculate 3 or 4th order derivative by just I developed this from the central derivative formula. And what we actually encountered is that the error is so much high, and it's depend on how much slice you take.
Of course, the error always depends on how many points you take. And the trouble is with numerical, the formula for the derivatives, ultimately you should take a limit, right?
Right.
You cannot take a limit, so you take a small value of h. The smaller the value of h you take, the better your result should be. The trouble is, if you take too small a value of h, then floating point errors in calculation, rounding of errors, which are what they're usually called, they become more important. So you end up with
right.
ruining your result. So numerical derivatives, frankly, are things you should not do unless you're forced to.
Okay.
That has nothing to do with Python or Numpy or anything. That's a basic generic statement. Numerical derivatives you should do only if you have no other option. I just illustrated numerical derivatives because it's easy to illustrate and so on. Not really because it's a very useful mathematical technique.
Okay. So one more question. In integration, in other languages, we call a subroutine, and it is a sophisticated subroutine. The slicing is actually some kind. They are fitted in the subroutine, so the better result we got from this subroutine. And in this case, what if we call the scipy or other things, and all trapezoidal rule, we have to we have to put some differentiation. Difference, the h. So
no, okay, that's because I was only showing you traps and sims.
Yes.
There are other methods like QAD, which actually uses adaptive Gauss-Cronrod quadrature. That's a huge mouthful, but that is one of the best methods. In fact, frankly, this quad essentially uses exactly the same numerical algorithm that the best Fortran subroutines use. You may have heard of QuadPack, which is basically the best integration subroutine available for mathematical usage. And that QuadPack is basically implemented in the quad function. So what happens is that you first divide you do 5-point Gauss quadrature and 11 point, or say use not 5, maybe 7-point and 15-point. 7-point Gauss quadrature, 15-point something called Gauss-Cronrod quadrature. Doesn't matter what the details are. Estimate the error from that. The error is too big. You divide the interval in 2 pieces. Go again until the error becomes small enough. So that's exactly the kind of thing which other languages also implement. But that's what you use. So in actual use, you would use something like traps. You would use sims. When would you use quad or sims? You would use traps or you would use quad. You would use traps or sims when the function is not available to you. What is available are the values. In many cases, you want to find the area under an experimental curve. And only the function values are available to you. Then you cannot subdivide and get more accurate results. And the result is whatever you have.
Right.
Okay, there's one question: would use of so many modules built in Python result in degradation of logical sense in building programming codes? That depends. Just because you might even argue that just because I have a nice knife, I'm actually losing out my ability to use my hands to create tools. Human civilization has advanced by using higher and higher and better things. If you just want to keep on using Stone Age tools just because of some philosophical reason, by all means do it, but I think that would be stupid. Of course, not learning the program at all would be bad. That's why we insist that you learn Numpy, not scipy first. You learn Numpy, learn to write the codes using that. With Numpy, you can avoid writing explicit for loops, but those loops are there. They're very much there in front of you. And you are actually thinking in terms of them. And of course, once you have learned all that, you can go ahead and use your in practical applications. Would you write a NumPy code every time you wanted to integrate something? I don't think you would. That would be again rather stupid. There are two things. One is learning the thing, for which, of course, you have to learn the basics. For that, Python actually is a full. I think one thing which people confuse here is because Python has a lot of modules which does various jobs for it. That doesn't mean that it's not a general purpose programming language. It's just a general purpose lower order programming language like any other language. You want to learn standard programming using any other language's specs, you can do it here and you can do it much more easily, for the simple reason that all the kind of overheads which ordinary older languages used to have, Python doesn't have, simply because Python has the advantage of being newer, so they just learn from those languages. However, once you have those, would you still want to keep on using? Just like somebody right now talked about numerical integration module, which Fortran has, for example, in the Quad Pack or BUS. Anybody using actual numerical integration would not write his own code. He would rely on something which experts have written, simply because that frees up time for doing other more productive work. So you learn how to integrate, but you also learn how to use a Swiss knife.
Right. Okay. Thank you, sir.
Excuse me.
Yeah.
Can we use symbolic Python to you and to integrate analytically? Here we in numerical integration, there are some errors. Can we avoid those errors in
I guess,
symbolic
are you
Python?
asking of symbolic integration?
Yeah, symbolic integration
That
in
will be
using SymPy.
that will be the next topic.
Okay, thank you, sir.
Yeah,
Thank you.
that will be the next
Okay.
I'm not sure whether you will talk only about integration, but anyway, definitely about integration as well.
Okay, thank you, sir.
Ranjan Das has a question. Taking derivatives of polynomial interpolation formulas may be a better approximation for higher order derivatives. It's a comment, I think.
Yeah, that's a comment that also depends strongly on what kind of functions you have. And that's not a universally correct statement. But frankly, there is no one perfect answer for all numerical problems. If that had been the case, then frankly, we would not have had a numerical answers course any longer in universities. We would have just asked people to, somebody would have written a program which would have done everything perfectly. Most of these statements that people make about this being better than the other depends on certain assumptions about the functions. And the reason why you need to learn numerical integration, numerical analysis properly is to understand when to use something and when to not use something. So, higher order derivatives, frankly, are always bad unless you have if you have a point function which is really well approximated by polynomial. Higher order derivatives would be good using the polynomial interpolation. Then there are other problems. For example, polynomial interpolations actually become very bad for many functions. And in fact, they become worse with more if you increase the number of points. That's something called the Rumia phenomenon. These are technical details, and these. So the short answer is there is no uniformly good way. For certain functions, that what you are suggesting is actually good. For certain other functions, it's actually very bad. And that's why you need to know something more about the mathematics to be able to really use numerical computation. It's not just blindly using the computer.
I think we should resume the session, and I request Arunabodha to take over.
Okay, so I will stop presenting and